Okay, so previously I have my A equal to, let's see if I have my command history. Yeah, let me just put n and delta x. And previously I have A equal to this. But now in the case of the backward difference scheme, my diagonal should be multiplied by plus 1 over delta x. Instead of having an upper diagonal, I'm supposed to have a lower diagonal. So instead of shifting by -1, I shift by +1, and instead of plus, I have minus. Right? So now if you look at the workspace, my A is going to have a positive diagonal and a negative subdiagonal, lower side of the diagonal. Okay? And in this case, if I plot the eigenvalues of not 2 times A, but just the eigenvalues of A, and let's do x is equal what? Okay, so what we see is that it's exactly the opposite of the previous case. The eigenvalues are not on the left side of the imaginary axis. They are flipped over to the positive side of the imaginary axis. What it means is that now my scheme is stable for A greater than 0, right? If A is greater than 0, remember we are multiplied by negative A times the matrix. So if A is positive, I now get negative eigenvalues. I can have a stable scheme. And vice versa, when A is less than 0, I get unstable. So this matrix means A less than 0, unstable. A greater than 0, stable. Again, if my delta t is less than delta x. Here I have a bug, should be delta x. Well, that's only for forward Euler, right? That's only for forward Euler. And if you use backward Euler or any implicit schemes, you may not have that restriction. If you use more complex advancing schemes, you may have a constant. Maybe delta t has to be less than 1.4 times delta x or something like that. If you use some of the more advanced time integration schemes, whose stability region looks different from forward Euler. All right. Okay. So now how about our final case, our central scheme? In our central scheme, let's just change things to over 2 delta x. And now I don't have a diagonal anymore. And I need to get the upper diagonal by circ shift by -1. Right, so this is my new A. Looks like that. All right. So basically, instead of 1,000, it has 500, right, to account for the 2 delta x, and the diagonal is 0. We have an upper and lower diagonal. So let's clear and plot now the eigenvalues. X is equal. Read. Here we are. What do we have here? We have a set of eigenvalues exactly on the imaginary axis. All right, and that's the only possible explanation for the scheme being kind of stable, both for A positive and A negative, right? So no matter if A is positive or negative, when you multiply by -A, we still have everything on the imaginary axis. Okay, and that also is an explanation for why, although the scheme is second order, it approximates the spatial derivative more accurately, which means at every step the error is small. I mean, the additional error is small. But because the resulting ODE is marginally stable, the error made by previous steps are not going to get diminished. It just accumulates more and more and more. So although the scheme is more accurate at a per time step level, the accumulated error is not necessarily smaller in some sense, right? So that's an explanation for, although we have a second order scheme, we have a first order scheme, the first order scheme actually commits more error per step. But at the end, it looks like similar. The amount of error looks similar to the second order scheme. I mean, depending on how you count for error, right? If you count for the error in the derivatives, the second order scheme actually gives you a lot more error than the first order scheme. All right. Yes?
Does this mean if you use the midpoint method for after you get this A with the central difference, use the midpoint method to like differentiate your t's? Would that be stable?
Yes, that's a very good point. So if you use the central difference to discretize space and then use a midpoint to discretize time, you actually get a stable scheme. You get a stable combination. While if you use one of these upwinded schemes, one-sided difference, there is no way you can get a stable solution using midpoint. All right. And as we're going to see later, most real differential equations are not going to be as simple as that. So you usually have other stuff come in. And midpoint time integration is usually not a very good choice if you have, I mean, it's only a very good choice if you only have this first order spatial derivative that gives you pure imaginary values.